So again in Lab 7, we're going to start with some simulations. So open up the 1100 folder and go into the Lab 7 folder. And there's 3 collision simulations that you're going to look at. So you open up the first one, and you need to write some stuff down before you start. This is actually started in your lab manual, is that you need to record the mass and the velocity of this guy and the mass and velocity of this guy. And then you'll calculate the momentum of this guy before the collision, the momentum of this one before the collision. And then when you run the simulation, the collision happens and you can stop it. And again, you need to write down the mass, which won't have changed, and the velocity after the collision, and the mass and velocity after the collision of this guy too. And again, you calculate their momentum before and after the collisions. Once you've done that, you're ready to move on to the next simulation. So we go to collision 2. In this one, they're going to be headed towards each other. The velocities point in opposite directions. So again, write down the mass and the velocity of this guy before the collision, mass and velocity of this guy before the collision. Run the simulation, and after the collision, stop it. And write down the velocity and the mass after the collision, the velocity and the mass after the collision. Calculate the momentums. So you'll have 4 momentum calculations, before for both masses and after for both masses. The only thing that's tricky about this one is that, remember, velocity is a vector. It's got a direction. That means momentum's also a vector. You need to keep track of the minus signs to get your numbers to work out. Then you can go on to collision 3. Again, these guys are pointed towards each other. Write down the mass and the velocity of this one before the collision, mass and velocity of this one before the collision. Run the simulation, and these guys just stop. So fine. Again, write down their masses and their velocities after the collision. Do all your calculations to find the momentums of these 2 guys before and after the collision. And again, because they started going in opposite directions, you need to keep track of the minus signs in order to get your values to work out correctly. On the next page, they say, what pattern do you notice in the collision? Hopefully it's going to be conservation of momentum. And then write out a mathematical equation that represents this pattern. So before I tell you how to use the equipment in Lab 7, I just want to point out something that's true in the manual for Lab 7. So for the first time ever, when they tell you to summarize your data in a table, they don't actually give you the table. You're expected to draw it in yourself. And likewise, with the conclusion, they no longer give you that bullet list of things that you're supposed to answer. You're expected to know how to write a conclusion yourself from now on. So that's going to be true for the rest of the semester, is that you'll have to write the conclusion without the bullet list and create your own tables. The reason why it's important for you to realize that now is that this is also going to be true in the lab exam, which is next week. So just make sure that you are aware of how to write a conclusion, how to write a data table, that sort of stuff. There is an information video online for the lab exam to help you prepare for it. I do recommend that you watch that early so that if you have some questions, you can find your lab instructor ahead of time and ask them. Okay, so now I will tell you about how to do the experiment. So to begin with, you're going to need to weigh your 2 carts. So the cart 1 is the one that's closest to the sensor. So you weigh cart 1, you weigh cart 2, and then you need to weigh them together. So you'd stack them like this on the scale and weigh them as one big chunk. And the reason why we do this is that then we know what the uncertainty of the total mass is. It's just the uncertainty of the electronic balance. So the next point is that I know I'm always hassling you guys to level your track carefully, but this is again another experiment where if you don't level the track very carefully, you find that you have a really terrible time getting good agreement between your values. So do it as carefully as you can. It makes a big difference to this experiment too. What we're going to be studying is an inelastic collision. So these 2 cars have been equipped with Velcro, so they actually stick together. So an elastic collision is a bouncy collision, they bounce apart. An inelastic collision is a sticky one, they stick together like this. Now theoretically, in an elastic collision, a bouncy one, you expect both momentum and kinetic energy to be conserved. That is, the total kinetic energy before and after the collision is the same, and the total momentum before and after the collision is the same. In an inelastic collision, a sticky one, we only expect momentum to be conserved. Kinetic energy is not conserved. The reason why is if you think about 2 balls of putty and you throw them together and they go splut and stick, some energy went into deforming the shape of those balls of putty. To a very minor extent, something similar is happening here with the Velcro hooks. The two carts crash together, they flex, and we lose a little bit of energy to that. We also lose a little bit of energy to the sound they make when they crunch together, but that can happen in a bouncy collision too. So the collision that we're going to be studying in this experiment is you'll have one cart about 2/3 of the way down the track and the other cart at the dead zone, the edge of the dead zone, and you're going to send this one down the track with some velocity. This one will remain stationary. They'll collide, stick together, and then continue the rest of the way down the track. And that's the motion that you want to capture on your screen. So just to demonstrate, you give this one a velocity, they stick together in the collision, and they continue on together. So the quantities you're going to be calculating in the end are going to be momentum and kinetic energy, and for both of those, because you've already got the masses involved, what you really need are the velocities of the single cart before the collision and the two carts together after the collision. So I'm going to show you on screen how you get the velocities before and after the collision using the program Velocity. Okay, this is what you're going to see on the screen when you do the collision experiment. So first of all, I just want to show you which program to use. Often we've been using acceleration. This week you want to go back and use the velocity program again. So that's the program we used in the very first lab. So open that guy up. That's the best one to use. You could also use the acceleration one, but this one gives you a bigger graph. I send one cart down the track about 1/3 of the way. It collides with the second cart, which is stationary, and then they stick together and continue on. So this is what that looks like in real time. All right, so this is the bounce back at the end of the track. We want to ignore everything here. So this kink here, this is our collision point. So we're going to need the velocity of the carts before and after. So this is the velocity of the one cart, and this is the velocity of both of them after they've stuck together. To get the best results, it really is best if you just highlight about 3 or 4 data points, not too many, right before or right after the collision. And the reason why is that there's a slight bit of friction here, and that can really screw up your results. So it's actually best, you'll get the best agreement if you only highlight a very small amount of data right before and right after the collision. So we want the fit on this, so I've highlighted the data I'm interested in. I go fit, linear fit, move that somewhere sensible, and then I would print this out. So I'm going to want that. And then I do it again for just about 3 data points right after the collision and print this out as well. So that gives me my velocity before for one cart and after for both carts stuck together. And I've already got the masses of the two carts, and then I can go on to calculate the momentum before the collision, the total momentum, its uncertainty, the momentum after the collision and its uncertainty, and then I'll do a percent difference before and after for the momentums, and summarize everything in a table, write a conclusion, and then carry on, because the next part is to calculate the kinetic energy before the collision, its uncertainty, the kinetic energy after the collision and its uncertainty, and then again we do a percent difference to compare the two, summarize, write a conclusion. The only thing that's tricky about that second one is, remember, this is an inelastic collision. We don't expect kinetic energy to be conserved. So just be careful about that one. Think carefully about what the theory predicts and what your results mean relative to the theory.